Good morning, students. Welcome back to the online class. Today, in the topic of magnetic effect of current, I'm going to take up the topic which I've explained in my previous class. The topic is magnetic field due to a current carrying circular coil. Now, if you look at the diagram number 1, it is actually a cardboard. Through this cardboard, a circular loop has been passed. The current is going to enter from point P and it is coming out from point Q. In the figure number 2, again it's a cardboard. It is again a circular loop, but now the current is going to come through Q and coming out from P. As we have studied in the previous video, when the current passes through the coil, a magnetic field will be produced around the point P as well as around the point Q. This P will have an anti-clockwise magnetic field according to the Maxwell right-hand thumb rule, and this point Q will have a clockwise magnetic field again by the same rule. Now we are already knowing that these rings will be concentric rings. The same thing is going to happen in the diagram number 2. But here, if you look at the diagram properly, at the point Q, we are going to have an anti-clockwise magnetic field, and at the point P, we will have clockwise magnetic field. Now, to know further in this topic, we have clock rule, and the rule says that if looking at the face of the loops, if the current around the face is in anti-clockwise direction, the face has north polarity, while if the current at the face is in clockwise direction, the face has south polarity. Now, on the basis of this rule, if we look at the diagram number 1 once more, we will find out that at this end, the magnetic field is anti-clockwise. Now the clock rule says that if there is anti-clockwise, then it will have a north pole, and if it has got a clockwise magnetic field, it will have a south pole. So in the figure 1, at P it was anti-clockwise, so it is north pole at P, and obviously at the Q it will be having south pole. In figure number 2, here at Q it is anti-clockwise, so it will be north pole at Q and south pole at P. If you look at both the diagrams, here the current was going to enter from P coming out from Q, whereas in the figure number 2 the current was going from Q coming out from P, and in both the cases we can find out the polarity has been changed. Here P was north pole, Q was south pole. Here P is south pole and Q is north pole, and this has been obtained by the clock rule. So if you look at the diagram here, wherever we have a magnetic field of clockwise nature, it will create a south polarity, and whenever we have a magnetic field of anti-clockwise nature, it will create a north pole, and that is the clock rule. Moving forward to the next topic of today, and the topic is magnetic field due to solenoid current carrying current. And the definition is, if an insulated wire is wounded in form of a cylinder coil whose diameter is less in comparison to the length, the coil is called a solenoid. And this insulated wire is winded on a cylindrical coil, and this is a very important point, whose diameter is less in comparison to the length of the coil. That arrangement will be known as solenoid. When the current is passed through a solenoid, a magnetic field is produced around it. The electric current in each circular loop of a solenoid flows in the same direction. The magnetic fields of all the loops add up to make solenoid act as a bar magnet for any point outside it. One end of the current carrying solenoid acts as north pole while the other end as a south pole. Now let me clear it by a diagram here. Now this is a solenoid. As the diagram can be explained properly, it is a cylinder, hollow cylinder, on which insulated copper wires are winded. Now when the current is passed through this insulated copper wire, as we know, a magnetic field will be current produced around this wire. Now the statement says the end of the solenoid at which current flows in an anti-clockwise direction acts as north pole, while the end at which current flows in clockwise direction acts as south pole. Now this rule says that if we take up the solenoid here and if we look at the diagram properly, the current is now going to enter from here. It is coming out from here. Here the current is flowing in an anti-clockwise direction. So when it is moving in an anti-clockwise direction, then according to the clock rule, anti-clockwise direction we have a north pole. So in this figure, this solenoid will have a north pole at this end and south pole at this end. Now if we talk about the magnetic field produced by the solenoid, we will take up a diagram here. Since it is becoming a magnet, it is similar to the bar magnet. And if we draw the magnetic field lines around a solenoid, we can see here they are originating from the north pole and coming to at the south pole outside the magnet. Inside the magnet they are going from south to north. So this is very similar to the diagram which we have drawn in bar magnet. So whenever we pass the current through a solenoid, this will create a magnet, and the magnet will be similar as the nature of the bar magnet, and the magnetic field lines will be similar to this diagram. Wherever we have an anti-clockwise flow of current, we have a north pole, and vice versa we have a south pole here. And so if you look at the statement here, the end of the solenoid at which current flows in an anti-clockwise direction acts as north pole, while the end at which current flows in clockwise direction acts as south pole. Now coming to the characteristics of the magnetic field of a solenoid, point number 1, the magnetic field lines inside the solenoid are nearly straight and parallel to the solenoid. It means that if you look at the diagram here properly, these lines which are going from south to north inside the magnet, inside the solenoid, they are parallel to each other and they will not intersect. That is the point number 1. Point number 2 says the magnetic field lines become strong on increase the current in it. So if we increase the amount of current in the solenoid, the strength of the magnetic field increase. That is the point number 2. Point number 3 says the magnetic field is increased if the number of turns in the solenoid of given length is increased. So if we increase the number of turns in the solenoid, obviously the strength of the magnetic field will be increased. And then coming to the last point, the magnetic field is also increased if soft iron core is placed along the axis of the solenoid. Means if you want to have a very strong magnetic field by a solenoid, then the hollow space which is there in this cylinder should be filled up with soft iron core. And when you put this soft iron core, this will increase the magnetic field of the solenoid. So there are 4 characteristics of the magnetic field produced by the solenoid. If we increase the current, solenoid will have a stronger field. If we increase the number of turns, it will have again a stronger field. And last one is very unique. If we put an soft iron core inside the hollow space, the magnetic strength will be increased. So coming to the diagram of the solenoid, the looping of the solenoid is very important. Here the looping is anti-clockwise. So this end will have a north and this will have a south. And when we draw the diagram of the magnetic field, we will have the diagram like this. So this is what we have in today's video. I hope you have understood the topic of solenoid and the characteristic of the magnetic field produced by the solenoid. In the next class, we will take up some more topic of this chapter. So thank you and have a nice day.